Hello everyone, I hope you're all doing well. So we're going to start a new chapter in our life today. This is going to be rigid body kinematics. Okay, it's a very brief introduction to rigid body kinematics. So first of all, we will start off with what is meant by a rigid body. Okay, so which we already know from statics. Okay, so rigid body is something that does not undergo large or finite deformations when forces are acting on it. Okay, so rigid body does not. So a body that does not undergo large or finite deformations when acted upon by forces. Okay, so which means that the strains that you see in a rigid body are probably infinitesimal strains. Okay, or the small strain theory can be applied for rigid bodies, which you might have typically come across in mechanics of materials. All right, we are interested in rigid body motion. Okay, and then rigid body motion can be split into the following cases. Okay, so rigid body motion. Okay, I can split this into the following cases, and let me, as I'm looking at the cases, let me also draw a figure and then show you what those cases are. Okay, so I could have a situation of rectilinear translation. Okay, now if I have rectilinear translation, let's consider that I have a rigid body right here. Okay, so this is some kind of a potato shape. Okay, let me choose 2 points on this rigid body. Okay, so let me call this as point A, and then this is point B, and then let me join them by a straight line. Okay, let's say that this is a dotted line here. Okay, so if this body is performing translation, then what's going to happen is that if this is the position of the body at time t, so if this is the body at time t, let me bring back, so at time t, then if I take this body and look at it at time t plus dt, right, after an infinitesimal amount of time has passed, what's going to happen is that this body would have just translated in the following manner, okay, along a straight line path. Let me bring that down here, and likewise for this guy here, getting to be a sticky customer. Okay, so it would have traveled along a straight line path, and that path is just essentially shown here. Okay, so this is just a straight line path here, and so this is going to be the idea of rectilinear translation. Essentially, I'm just traveling in a car along a straight line. A car is a rigid body, so I'm just going from one point to the other in a straight line path. Okay, so this is at time t plus dt is what I have here, t plus dt. Okay, and then this is the direction of motion. Rectilinear translation is probably the easiest or the simplest case of rigid body motion. I could also have a situation of curvilinear translation, so that is B. Okay, in curvilinear translation, what do I have? I have a similar situation. Okay, so I'm going to copy my figure from here. Okay, and then put that here. Maybe let me get rid of my lines. Okay, and then I'm going to copy this guy as well. Okay, and maybe all my labels too. This is fairly convenient. I can copy all my labels too. Then I'm going to copy this creature here as well. Okay, and then I'm going to put that somewhere here, get rid of some of these extra things, and so on. I guess that was not my intention. So let me bring this down here. Let me bring this, keep that there, and then let me bring that down there. Okay, so in curvilinear translation, what's going to happen is that these bodies will still be traveling in a way such that there is no rotation of the body, but it is just that they would be traveling along a curved path. Okay, so which means that if I trace out the movement of the point B, it's going to be along a curved path, and then point A is also going to be along a parallel curved path. Okay, so probably something of this nature. Let's see. Okay, so I guess I wanted to draw it as a curve, so something of that kind. And and this is also going to be something of that kind. Okay, so let me draw these as dotted lines as well. And so I hope the idea is fairly straightforward, right? I mean, these are all traveling along this curved path, not along a straight line path, but there is still no rotation of the body. That is the important thing when I'm looking at a rectilinear translation or curvilinear translation. Okay, the angular velocity of the body has not come into play yet. Then I go to the third case of motion, which is going to be fixed axis rotation. Okay, so in fixed axis rotation, I essentially have the rigid body rotating about a certain fixed line or an axis passing through its body, or it may be outside the body. It does not matter where it is. Okay, so if I take a look at the rigid body, let's say that this is the rigid body at time t. Okay, so this is at time t. Okay, then let's say that the rigid body is rotating about some kind of a pivot point on this body. Okay, what's going to happen is the following. So if I look at the body after time t plus dt, let me copy this figure. I'm going to do a few things here. Bear with me for a minute. Okay, I'm going to cut that off. And then I want to twist this guy. Okay, and then I want to come and bring that down here. Okay, so what I'm showing is that initially there would have been a straight line. If I had looked at the body initially, there would have been a straight line, but then because of the fact that this body has rotated, this line would have now rotated as well. Okay, so this line would have rotated because of the fact that the body is rotating. Okay, and so this is going to be the situation at time t plus dt. Okay, and then I can draw this as a dotted line so as to show you that, okay, at time t plus dt it has rotated now. Okay, so there is a certain angular velocity for the body in this situation. All right, then we have a combination of all of these cases, which is called as general planar motion. Okay, and then of course one thing that I want to write down here before I go on is we're going to be focusing on 2D motion only. Okay, so that's our focus. That's the limitation or the scope of our subject or the scope of our course. Okay, so this is part D is general planar motion. Let me write my E carefully. All right, what do I have in general planar motion? The idea is fairly straightforward. I take a rigid body. Okay, let's say that here was a line that I had marked on this rigid body, point A to point B. So let's say that this was the line that I had marked on this rigid body. Let me draw this as a dotted line. Okay, so this was A, and then this was B. Okay, and let me make sure that I have enough space to draw some lines if I need to. Okay, so this is at time t. At time t, then let's say at time t plus dt, here is where the body is. Okay, so I'm going to take this body, I'm going to copy that, and then I'm going to paste it and then rotate it a little bit and then bring it out here. So here is what is going to happen at time t plus dt. What would have happened is that, okay, this is at time t plus dt, and likewise I have it there as well. What would have happened is that this point A and then this point B would have actually traveled along a straight line path, okay, or a curvilinear path, depending on what the path is. So probably, let's say that, this was the path traveled, which means that after time t plus dt, there is a translation taking place and also a rotation has taken place. A fixed axis rotation has taken place, because as you can see, this would have been the situation right after time t plus dt, but then it is also rotated a little bit, right? So which means that there is also a rotation that is taking place along with general translation. Okay, so this is called as general planar motion. Okay, so general planar motion, I'm going to write this down here. So general planar motion is a combination of translation plus fixed axis rotation. Okay, and this is a famous theorem in dynamics. This is called as Chayle's theorem, Chayle's theorem or Euler's theorem. It's the same. I think they use it interchangeably. Okay, so this is called as Chayle's theorem or Euler's theorem. Okay, and so this is the way we are going to handle our problems as well. Okay, we are going to be looking at general planar motion. Look at it as a combination of some translation and some rotation. The translation can be curvilinear or rectilinear. Okay, all right. So to end this particular very short talk, and I'm going to look at the concept of angular velocity and angular acceleration of a rigid body. Okay, so angular velocity which is omega vector, and angular acceleration which I'm going to call as alpha. Okay, and to understand this or to motivate this, I'm going to just consider some random rigid body. Let's say that I have some kind of a reference line here which I'm drawing, some fixed line on the ground. Okay, and I have a rigid body. Okay, so this is a rigid body, and on this rigid body I'm going to draw two lines. Okay, so here is one line which I'm going to call as line AB. Okay, and then here is another line which I'm going to call as line CD. Okay, so this is A, this is B, this is C, this is D. Okay, so these are like 4 points on this rigid body, and as you know that since it's a rigid body, these points will not be traveling too far away from each other if the forces have been applied on the body. The deformations are infinitesimal. Okay, so this is, let us say, the position of the rigid body at some time t. At time t, the rigid body is sitting here, and then let's say that this angle between these two lines, let me call that angle as some angle beta. Okay, and let's say that the angle made by this line AB with the reference line. So if necessary, here is what we can also do. Okay, so I can continue drawing this, and then I can continue drawing this as well. Okay, so if you want to look at it this way, maybe I can keep this fixed here. So the angle made by this line AB with respect to the reference line, so this is a reference. Okay, I'm going to call this angle as some angle theta. Okay, this is at some time t. Then let's say, okay, what's going to happen at some time t plus dt? I'm going to take all of these guys. Okay, not all of that, but just all of this. I'm going to copy that and then clear up some of these things. I'm going to just keep this here and then keep this here. Okay, so I'm going to take this guy, and then after time t plus dt, what's going to happen is that probably this rigid body would have undergone some kind of a general planar motion. I don't know, maybe it is sitting somewhere here. So this is at time t plus dt. It should be the same size as that one. Okay, so this is good. So at time t plus dt, it has traveled from here to there. Okay, so general motion. This is general planar motion. So this is at time t plus dt. Now, if I look at the angle made by AB with respect to the reference, look at this. So I take this line here and then I bring it down here. This angle has now changed. Okay, and I'm going to say that the change is an amount of d theta. Okay, so this angle is now going to be theta plus d theta. But you see, the angle between the line AB and the CD has not changed. Okay, so that is something that is very important to see here. And then we define the concept of angular velocity. Okay, so angular velocity which I'm going to call as omega. Okay, so this is I'm going to say, okay, what is the angular velocity of the line AB? Okay, so angular velocity in general is defined as the rate of change of the angular displacement. Okay, this is the definition typically. If I look at the angular velocity of the line AB, right, what is this going to be? This is going to be the change in the angle with respect to the reference over time, right? So this is going to be theta plus d theta minus theta divided by the time interval that is taken. So that is t plus dt minus t, which means that omega AB is going to be d theta by dt, at least in the point of view of the magnitude. Okay, what about omega CD? Is going to be the same as omega AB because the angle between AB and CD remains fixed since it's a rigid body. So the fundamental byline is that any line on the rigid body will have undergone the same angular velocity over this time dt. Okay, so which means that any line on the rigid body will have the same angular velocity, which means that angular velocity is actually a property of the rigid body as a whole. Okay, so which means that angular velocity is a property of the rigid body. Okay, which means that I take any line on the rigid body, if I look at its angular velocity, it's going to be the same as the rigid body. Okay, so which means that any line's angular velocity of the body is the same as the angular velocity of any line on the body. Okay, and angular velocity of course is a vector. Okay, so which means that by definition we can write the angular velocity vector as the rate of change of the angular displacement vector. Okay, and as you can see here, the angular displacement vector is going to be coming out of the page, in the counterclockwise direction. So I can write this as omega k, depending on what coordinate frame I take. But the moral of the story is this. So for us in 2D motion, omega is either into the page or out of the page. Okay, so omega is always going to be in the direction perpendicular to the direct plane of motion. Okay, so in 2D motion, omega is always perpendicular to the plane of the motion. Okay, this is a very, very important thing to understand. Okay, because the confusion happens when we do 3D dynamics, which we are not going to be doing in this class anyways. But the idea is, if I'm doing 2D dynamics, what is the direction of omega? It's either into the page or out of the page, nothing else. Okay, and then very lastly, I can define angular acceleration vector. Okay, so let me write this properly. This is angular acceleration alpha is the rate of change of the angular velocity vector. Okay, so this is also a property of the body. Okay, so which means that both omega and alpha are properties of the rigid body. Okay, so this is the basic idea, and for any typical rigid body, so we would typically draw this as draw some arbitrary potato shape, and then I would say, okay, Okay, this is the direction of omega. Okay, I don't know what the direction of alpha is. It could be the same as omega, or it could be opposite to omega. It doesn't know. If it is starting off in an arbitrary fashion, that would be the representation of alpha. So some kind of a generic representation. Okay, so generic representation. Okay, and so once again alpha and omega, so which means that both alpha and omega are perpendicular to the plane of motion. That is one thing. Alpha need not be in the same direction of omega. It could be in the opposite direction. This depends on the problem. Okay. All right. So a very brief summary is that if I go back and look at rigid body, what is a rigid body? Definition of rigid body. You know this from statics. You are applying this in probably strength of materials or mechanics of materials. And we're going to be making use of this in dynamics as well. What are the types of motion of rigid bodies? Rectilinear translation, curvilinear translation, straight line motion along a curve, fixed axis rotation. There is no translation, but there is only rotation here. And then I have general planar motion, which is the most general case of all, where it's a combination of translation and fixed axis rotation. Okay. Concept of angular velocity. Angular velocity is a property of the body as a whole. Okay. So if I take any line on the body, its angular velocity is going to be the same as the angular velocity of the body. And angular velocity is always going to be in a direction perpendicular to the plane of motion. Likewise, here is also the situation. This is also the same in 2D motion. Okay, so in 2D motion, okay, 2D motion, my D did not come out too well, but well, that's even worse. Okay, so in 2D motion, both alpha and omega are perpendicular to the plane of motion. Alpha need not be in the same direction as omega, could be opposite omega as well. All right, thank you very much. Stay safe, all of you. Bye-bye.